The early history of the heavy, self-propelled anti-tank gun, later known under the names Ferdinand and Elefant, developed amid a rapidly changing situation as the German army sought to devise an adequate response to the growing diversity and quality of Soviet armored vehicles. At the beginning of 1940, German requirements for combat vehicles remained relatively moderate. It was assumed that a mass of 30 tons could achieve a balance between mobility, armor, and firepower. German designers adhered to this framework, although trends toward creating increasingly heavier vehicles were already noticeable. The competitive environment between the Porsche and Henschel firms seemed a stimulus for technical progress, but in reality, it led to significant resource expenditures, duplication of efforts, and accumulation of technical solutions that did not always meet the real needs of the front. The development of the vehicle that subsequently received the name Ferdinand was a direct consequence of an attempt to combine theoretical engineering solutions, which had gained some notoriety in the late 1930s, with political expectations that were sometimes perceived by the command as mandatory for implementation. Since the Porsche firm had already invested significant resources in the VK 45.01P heavy tank project, halting work without attempting to utilize the ready-made components appeared, from the perspective of German military economy, an unacceptable luxury. For this reason, the hull, designed for an entirely different layout, was selected as the base for the future heavy tank destroyer at a stage when the purpose of this equipment lacked a clear doctrinal alignment. And herein lies the first systemic error. The vehicle was not designed to fit the assigned task, but rather the task was adjusted to fit the existing design constraints. The idea of placing two gasoline engines in the forward section, transmitting torque to generators and then to electric motors mounted on the sides of the rear hull, appeared promising in theory. Porsche designers viewed this principle as a way to reduce the likelihood of mechanical transmission failures and lessen the load on the driver mechanic. However, practical tests quickly revealed that the gasoline-electric scheme created its own set of risks, including component overheating, low tolerance for voltage fluctuations, increased susceptibility to damage from hull vibrations, and extremely inconvenient access to most assemblies. The internal space, formerly quite voluminous, proved so overloaded with cable lines, distribution blocks, and protective casings that servicing the electric motors in field conditions required disassembling part of the rear compartment almost down to the frame. Technical documentation from that period indicates that a full inspection of the electrical installation sometimes required more than 6 hours of work by 2 mechanics, with access to individual units possible only after removing additional armor plates. By mid-1941, the situation had changed. Encounters with the T-34 and KV-1 demonstrated that previous German anti-tank assets had become obsolete faster than anticipated. Powerful engines, sloped armor, and wider tracks on Soviet tanks posed serious difficulties for German forces. The response was a sharp escalation in technical requirements, initiated personally by Hitler. He demanded the use of a long-barreled 88mm gun, capable of engaging at ranges exceeding those of most existing tank guns. This requirement altered the very structure of future vehicles and necessitated an increase in mass, hull volume, and production capacities. The Porsche project found itself at the center of this transformation. He decided to retain his developed gasoline-electric scheme, which involved installing 2 internal combustion engines to drive generators, which in turn powered 2 electric motors connected to the drive wheels. The scheme appeared attractive for a tank weighing up to 30 tons, but after the requirements changed, the vehicle grew nearly twice as heavy. Nevertheless, Porsche was unwilling to abandon his own concept, hoping that its advantages, absence of a complex mechanical gearbox, and smoother power distribution would compensate for operational complexities. In practice, the system proved unsuitable for such loads. Overheating, high fuel consumption, and the need for precise tuning of electrical equipment made the design extremely sensitive to dust, moisture, and damage. When both competing prototypes were demonstrated to Hitler in April 1942, it became evident that the Henschel project was more reliable and technologically feasible. Workers and engineers noted that the heavy but still conventional mechanical transmission of the Henschel design coped better with the new requirements. The Porsche vehicle, in contrast, regularly stalled and overheated without apparent cause, while replacement and maintenance of components required more time and expertise. Despite the rejection of the Porsche project, production of 100 chassis was already in full swing, in anticipation of victory in the competition. Germany could not afford to simply set these hulls aside. Shortages of steel, lack of available production lines, and growing needs on the Eastern Front prompted the command to seek alternative applications. The compromise solution was to convert these chassis into heavy tank destroyers. They were fitted with a massive casemate mounting the latest 8.8 cm PK-43-2 L71 anti-tank gun, distinguished by a significantly higher muzzle velocity compared to the gun mounted on the Tiger I. The effective engagement range increased to values exceeding most contemporaries. The combination of the gun and 200 mm frontal armor made the new vehicle a potentially dangerous opponent for any existing equipment. German specialists of the time viewed it as a solution to a local but critically important task: breaching strong enemy defensive nodes and destroying tanks at long ranges. However, caveats were immediately noted. The vehicle's mass of 65-70 tons made it extremely immobile. The infrastructure on the Eastern Front was not improving, and bridges capable of supporting such a load were almost non-existent. It was assumed that the tank destroyer would become part of a limited set of heavy assets and operate within specially prepared units, where engineering support could compensate for design shortcomings. But frontline reality rarely allowed equipment to be used strictly according to instructions. Even at the planning stage, it became clear that these vehicles would end up in conditions for which they were not intended. By the time the decision was made to mount the 8.8 cm PK-43-2 L71 anti-tank gun on this hull, the project had already lost maneuverability in an engineering sense. The enormous barrel length required a stable platform, and the mass of the entire installation forced engineers to redistribute internal volumes, sacrificing crew comfort and increasing stress on the suspension. Here emerged the next systemic issue. The torsion bar suspension employed was not designed for significantly exceeding the original mass, and reinforcing individual elements only increased ride stiffness without resolving the root problem of lacking strength reserve. Tests at proving grounds showed that the average operating time of the running gear before the first failures of road wheels or torsion bars was significantly below standards, and during intensive jerks or sharp maneuvers, partial track misalignments occurred, requiring manual correction. Nevertheless, the command deemed the armor protection sufficient grounds for launching the vehicle into production. The 200 mm frontal plate was presented as an absolute argument in favor of the entire design's survivability, and although calculations indeed showed that most contemporary anti-tank guns, Soviet as well as Anglo-American, could not penetrate such protection at any practical ranges, this confidence created a false sense of universality. External protection concealed internal engineering risks, which manifested not suddenly, but as a consistent degradation of all systems when moving over rough terrain. Testimonies from mechanics, preserved in repair unit logs, noted that after every 10 to 15 km of march, the generator temperature consistently exceeded standard values, and the engine cooling systems sometimes failed to cope with the load even after an hour of continuous movement over soft ground. The gun, in contrast, demonstrated exceptional ballistic characteristics. The PAK-43-2 could penetrate most existing tanks at distances considered safe for equipment under its sights. The muzzle velocity exceeded that of other 88mm systems used at the time, and the quality of German optics ensured confident engagement at ranges where the enemy could not yet open effective return fire. For this reason, developers viewed the Ferdinand as a means of breaching defenses and subsequently destroying deep echelons of enemy armored vehicles. But the doctrinal setup directly contradicted the vehicle's actual mobility. For effective long-range employment, the crew needed to rapidly change positions after each salvo detected by the enemy. In Eastern Front conditions, where flanking maneuvers and counterattacks were commonplace, the heavy, cumbersome vehicle became a stationary target immediately after losing the ability to quickly reposition. The situation was exacerbated by the absence of built-in close defense armament. The omission of a hull-mounted machine gun was considered a temporary measure until hull modifications, but due to haste, this measure was never reversed. The only hope remained in mutual cover within mixed units, but in practice, infantry lagged behind, avoiding artillery fire that inevitably concentrated around large stationary targets. This created a situation for crews where every halt could lead to defeat by enemy assault groups. Preserved crew descriptions indicate that during the Kursk operation, they constantly felt threatened not so much by tanks or anti-tank guns as by infantry with grenades and incendiary bottles. The heavy gun could not be depressed low enough to effectively engage targets at minimal ranges, and narrow fields of view made the situation even more dangerous. In spring 1943, after the accelerated formation of 2 battalions, the new vehicles received the designation Ferdinand. Crew training was conducted on compressed timelines. The fire control system was precise, but demanding on the gunner's experience. The electromechanical part required constant attention from the driver mechanic and electrician. Training proceeded simultaneously with refinements to individual mechanisms, leading to a disconnect between theory and practice. Despite this, the vehicles were sent to the front. There was no time for delays. Operation Citadel, intended as a major offensive to encircle Soviet forces in the Kursk salient, determined the future fate of the Ferdinands. Nearly all produced vehicles were concentrated on a limited sector of the front. The command hoped that their powerful frontal armor and long-range gun would allow breaching the Soviet defense, saturated with numerous firing points. On paper, the plan appeared rational. The tank destroyers were to advance in the first line, destroying targets that could not be engaged by lighter vehicles, followed by motorized infantry and tanks to consolidate the gains. The first days of the offensive revealed the potential while simultaneously highlighting the limits of these vehicles' suitability. At long ranges, their fire was extraordinarily effective. Units reported destroying Soviet tanks before they could return fire. The gun penetrated the armor of any vehicles, including heavy designs, and did so from distances exceeding the tactical depth of enemy battle formations. Not a single T-34 or KV-1 could count on victory in a head-on confrontation in open terrain. The problem was that open terrain ended quickly. Soviet forces had prepared a deep echelon defense saturated with minefields. The Ferdinands, advancing through narrow passages, were mined more frequently than any other German vehicles. Their mass made any detonation almost a guaranteed damage to the running gear. Even minor track displacement led to a halt. The crew's own repair means were limited. Some vehicles remained in no man's land, others in craters, others on log obstacles. Recovery tanks could not approach under fire to these massive stationary targets, and crews were forced to destroy them to prevent leaving functional guns and equipment to the enemy. In addition to all this were the problems of the design itself. The electrical part, located in the middle of the vehicle, gradually failed under vibrations and sharp temperature fluctuations. Field mechanics complained about the impossibility of fixing malfunctions without dismantling large modules. Hot exhaust air from the engines overheated the fighting compartment, impairing crew concentration. In prolonged combat conditions, the temperature inside the hull could exceed permissible values, and crews, despite sealing and ventilation, regularly reported dizziness and smoke. Visibility was unsatisfactory. The limited number of viewing devices allowed monitoring only a narrow sector ahead of the vehicle, and any movement of Allied infantry created an impression of chaos, as the commander could not assess the situation beyond the sides. The situation was worsened by the fact that the Ferdinands lacked built-in machine guns, leaving the vehicle defenseless at close ranges. The crew could use personal weapons, but its practical value in combat was minimal. Infantry advancing with the vehicle often had to retreat under artillery fire, depriving crews of the ability to prevent enemy attacks from the flanks. Despite this, individual episodes of combat use showed that with proper employment, the vehicle could produce a serious tactical effect. Destroying fortified firing points, disrupting armored attacks at distant approaches, holding terrain sectors amid shortages of other heavy assets. All this became part of the short but eventful history of its employment. However, by the end of the first weeks of the offensive, it became clear that mechanical losses exceeded combat ones several times over. Of nearly 90 vehicles employed, only a few remained mobile. The reasons were varied. Some were mined, others broke down, others bogged down in the ground, and only a small portion were actually destroyed by enemy fire. When the first weeks of fighting at Kursk concluded, the degree of wear on the Ferdinands became evident. Even those vehicles that remained formally combat-ready required a full technical inspection. Crews reported that they could scarcely maintain the equipment in operational condition under continuous fire. Formally, it was assumed that after several days of combat, the battalions would be withdrawn deep to the rear for restoration work. But the development of Operation Citadel left no time for such luxury. Forward units retreated, rear roads became clogged with equipment withdrawing from the front, and any attempts to organize repair sites were blocked by the lack of safe space and shortages of recovery assets. Many Ferdinands ended up in what was called the Belt of Death, points where they could neither be used nor evacuated. Individual vehicles broke through several kilometers forward, but, deprived of infantry support, quickly became stationary targets. Crews described moments when, realizing the inevitability of capture, they were forced to destroy their own vehicles. This process was not simple. The charge had to be placed to destroy internal assemblies without leaving the enemy the possibility of restoration. Demolition was carried out after a thorough check of the ammunition to avoid uncontrolled detonation. Often, crews withdrew under fire, and some demolition teams were wounded during retreat. Statistics showed the majority of lost Ferdinands were destroyed in this manner. Those vehicles that were successfully withdrawn demonstrated a degree of damage not always attributable to enemy action. Electric generators failed after shock loads from nearby detonations, vibrations, sharp starts. electric motors broke down due to coil overheating, turning the vehicle into an immobile armored box. The internal combustion engine cooling system proved unadapted to prolonged operation in summer dust conditions, leading to overheating even during idling. Overheated engines could stall at critical moments. Cases were recorded in dozens, and in reports, driver mechanics detailed the circumstances: rough terrain, air temperature, duration of low-speed operation. The systemic nature of the problems became increasingly evident. However, the operation continued, and the surviving vehicles kept performing tasks. At the late stage of the offensive, the Ferdinands began to be used as stationary firing points. The command requested crews to occupy positions on heights where the firing range could be utilized most effectively. Due to limited mobility, changing positions took considerable time. The vehicle could bog down in soft ground, snag a track on roots or hidden logs, or come under crossfire. Nevertheless, in defense, they were dangerous. The enemy knew that any attempts to approach them frontally were doomed. Therefore, enemy infantry sought to flank, use terrain folds or artillery fire of high power. Among opponents, means were found capable of disabling the Ferdinand, though not in head-on combat. Massive 152mm howitzer shells, fired from long ranges, could destroy the running gear or damage casemate seams. A direct hit on the roof could penetrate the armor, as the roof of the vehicle had significantly less thickness than the front. One of the most notable incidents occurred when a Soviet Su-152 hit a Ferdinand from a distance of several kilometers, inflicting heavy damage. Despite this, the German vehicle managed to return fire and disable several SUs. Such episodes were perceived by crews as proof of the vehicle's potential, but did not change the overall picture. Any mobility or technical issues meant the loss of the vehicle. When combat operations began, all these factors combined into a whole. Actual loss data confirm that the majority of Ferdinands were not destroyed by enemy fire. They failed due to technical damage, were mined, bogged down in mud, or lost mobility due to power plant failures. Due to the vehicle's weight, evacuation was almost always impossible, and crews had to abandon them. This turned every advance into a forced competition between combat tasks and technical constraints. On paper, the vehicle could perform the functions of heavy assault artillery. In practice, every maneuvering attempt resulted in a new risk of losing the entire equipment. The battles at Kursk, which became the first major combat trial of the Ferdinands, exposed the full array of the vehicle's tactical limitations. In defensive positions, where they could occupy pre-prepared sectors and fire at long ranges, effectiveness was significant. But in the offensive, the situation unfolded differently. Breaching mine barriers proved an extremely difficult task for equipment weighing over 65 tons. Soviet minefields were saturated not only with anti-track, but also heavy high-explosive mines designed to halt tanks. A detonation under a Ferdinand led to damages that under normal conditions could be repaired by repair teams. But recovery required either powerful specialized equipment, which the Germans practically lacked, or several tractors linked together, making them vulnerable themselves. Therefore, even due to the mining of a single track, the vehicle became lost with high probability. In the first days of Operation Citadel, the majority of Ferdinands demonstrated impressive results in destroying Soviet tanks and anti-tank assets, but logistics and technical support could not keep up with the offensive pace. German engineering units failed to clear passages in time, and every vehicle halt increased the likelihood of defeat by either artillery or assault groups. In combat conditions, vehicles often had to move without infantry cover, depriving crews of the ability to prevent enemy flank attacks. By mid-operation, it became clear that the design did not allow using the Ferdinands as intended. Crews had already lost a significant number of vehicles, most of which were abandoned after technical failures or detonations. In practice, the same scenario repeated predictably. The vehicle successfully engaged targets, entered an active fire zone, performed several maneuvers, and then lost mobility. After that, the crew attempted to call for help, but evacuation opportunities were often absent. Regulations provided for the destruction of equipment if evacuation was impossible, and thus combat units effectively disabled costly and complex vehicles themselves. Evacuating vehicles damaged in areas saturated with artillery posed particular difficulty. Transporting a Ferdinand required either a FAMO recovery vehicle or several Tigers, which in conditions of heavy equipment shortages appeared wasteful. Moreover, recovery attempts drew Soviet artillery attention, and linked vehicles became ideal targets for batteries operating from pre-sighted positions. Therefore, most damaged Ferdinands remained on the front line. After the first weeks of fighting concluded, the remnants of the battalions were hastily withdrawn for repairs. An interesting pattern emerged. Combat damage constituted a minor portion of all malfunctions, while the overwhelming majority of vehicles required replacement of electric motors, generator repairs, running gear restoration, and engine maintenance. German engineers attempted to modernize individual systems directly in field conditions. On some vehicles, cooling system refinements were conducted, filters improved, and cable connections reworked. However, most recommendations compiled after the Battle of Kursk pertained to design issues that could not be eliminated in frontline conditions. Meanwhile, the strategic situation demanded new decisions from German command. Instead of writing off the equipment as uneconomical, it was decided to modernize the surviving vehicles. The modernization encompassed several directions. The hull received a machine gun mount in the frontal section. This was intended to partially solve the close defense problem. Commanders' cupolas were equipped with additional observation devices. Improvements also affected the engine transmission compartment. Structural elements were changed, mountings reinforced, and individual assemblies simplified. During modernization, the vehicles received a new designation, Elefant. Formally, this reflected a desire to distance from the original variant and emphasize a new stage of employment. Unofficially, crews noted that the renaming was a way to avoid negative associations attached to the vehicle. However, even after modernization, the Elefants remained vehicles with a narrow set of tasks, whose operational qualities significantly limited their use. The mass remained the same, meaning mobility and evacuation problems persisted. The electrical part, although subjected to certain refinements, still required constant monitoring. This meant that each vehicle needed a well-trained crew and access to qualified mechanics. In conditions of continuous fighting, such requirements became a luxury. It was precisely after analyzing the first weeks of employment that it became clear that armor and firepower, however outstanding, did not compensate for the fundamental engineering shortcomings of the entire vehicle. The command submitted requests to industry for hull rework, addition of close defense means, and improvement of the power section, but this required time. And time in 1943 worked against Germany. The first modernization decisions began to be implemented only after it became evident that further use of the original design in offensive operations was impossible. Thus emerged the program leading to the creation of the modernized Elefant variant, attempts to correct the most critical errors admitted in the initial project. The initial attempts to rework the design led engineers to an obvious conclusion. Without changing the internal layout of the power plant, eliminating most failures was impossible. However, this was unfeasible. They had to work within the existing hull, meaning engineering solutions were reduced to local improvements and reinforcement of those elements that failed most frequently. Problems related to generator overheating required increasing the cooling system's throughput, but the layout did not allow radical rework of air ducts, and engineers limited themselves to installing additional deflectors and minor changes to casings. This provided a reliability increase only in theory. In Eastern Front conditions, where dust, dirt, and fine debris constantly penetrated ventilation channels, these measures did not resolve the key problem: the initial unsuitability of the scheme for prolonged operation under high load. The PAK-43-2 gun, in contrast, required no substantial changes. Its strength characteristics and accuracy were superior to most artillery systems of the time. However, when mounted on an essentially makeshift superstructure, several operational difficulties arose. The weight of the gun mask and barrel length required constant adjustment of balancing mechanisms, and on each vehicle, after several shots, deviations appeared in horizontal aiming. These deviations were minor, but when firing at maximum ranges of 2 to 3 kilometers, any displacing factor became critical. Crews noted that attempting to quickly shift fire from one direction to another sometimes caused the casemate to vibrate, leading to momentary distortion of the aiming line. Restoring accuracy required recalibration, which was nearly unattainable in combat conditions. Although the remaining Ferdinands and later Elefants, by the end of 1943, could no longer influence strategic decisions, they continued to participate in battles as tools of local resistance, and it was in this capacity that their final capabilities and limitations manifested. The gradual retreat of German forces created conditions in which massive self-propelled guns became part of static fronts, or forced travelers dependent on rare sections of passable roads. In these circumstances, vehicles were no longer selecting positions, but rather tied to terrain where they could be kept operational. Sometimes this was the outskirts of small towns, sometimes railroad lines, sometimes hills or highway junctions. Reports indicate that crews themselves chose such points, trying, as much as possible, to position vehicles where they would provide some tactical benefit, rather than simply waiting for them to completely lose mobility. Most of these vehicles now bore traces of prolonged field repairs, welded seams over previous ones, replaced armor sheets, hasty temporary mounts. Inside, simplified connection schemes were increasingly encountered, where elements long out of order were disconnected to reduce circuit load. The fighting compartment floor was littered with remnants of thermal insulation soaked in oil, and the wall lining was covered with soot from endless overheating. Even when vehicles were not firing, the internal space filled with heavy fumes from spent oils and char. This was a sign of metal fatigue that could not be eliminated without major overhaul, already unattainable at the war's twilight. Nevertheless, German command continued to incorporate the Elefants into defense plans. They played a particular role in attempts to delay the advance of Soviet forces toward Berlin, when any large self-propelled guns acquired significance not so much as mobile elements, but as powerful stationary fire support nodes. If a position could be selected to exclude flanking maneuvers and force advancing troops into the frontal armor sector, the vehicles could hold the direction for some time. But such positions lasted briefly. After each battle, equipment lost operability even faster. Loads that a year earlier the vehicle could endure now became critical. What was once considered minor overheating or temporary failure now caused complete halts. And when such a halt occurred under fire, crews realized they had almost no time. Some Elefants were destroyed by their own crews before the enemy's approach, when it became clear that withdrawing the vehicles was impossible. Others continued firing until ammunition ran out. There were also those that essentially perished without external impact. Overheating led to cable ignition, and a fire erupted inside the vehicle that the crew could not localize. Considering the density of electrical system assemblies, a single temperature spike was enough for insulation to melt and the internal space to fill with thick, acrid smoke. When the last 4 vehicles found themselves south of Berlin, they represented more a residual embodiment of the idea than full-fledged combat units. The vehicles could fire and inflict damage on the enemy, but each shot and each meter of movement came at a cost impossible to compensate with repair or replenishment. In one of the final episodes, crews attempted to change position to avoid encirclement, but after several hundred meters, 2 Elefants halted due to electrical failure and engine overheating. They had to be destroyed on sight. The 2 remaining reached the city's outskirts and engaged in battle amid ruined buildings. Dense smoke, narrow streets, and the chaos of the war's final days made these battles brief and uncontrollable. The guns could still penetrate Soviet assault vehicles, but the lack of ability to change position quickly meant that return fire inevitably covered them. In the end, these vehicles too were destroyed by their own crews. By the time of Germany's capitulation, all operational Ferdinands and Elefants had vanished from the battlefield, leaving behind wreckage and fragments. Only 2 specimens survived the war intact, one in the USSR, the other in the USA. Their subsequent fate was typical for rare trophy equipment: demonstration trials, technical dissections, study of design features. Both examples later became museum exhibits, transformed into objects of study for historians and engineers. In these 2 hulls is concentrated the history of the entire project: ambitious, heavy, excessive, and at the same time unique. After all that has been said in the previous chapters, after the history of creation, first battles, technical compromises, astonishing victories, and agonizing failures, there remained one more side of the vehicle, the one that rarely made it into official reports and even less into post-war legends. From the outside, the Ferdinand indeed looked as if created for the war of the future. Monolithic front, high casemate, enormous tracks, and an almost mystical sense of invulnerability. But the deeper one looks into its structure, the more thoroughly one studies its inner life, the clearer it becomes. Beneath the massive armor plates hid a fragility incompatible with frontline reality. This was a paradox encased in metal, strength that could not exist on its own. The myth of super reliability rested solely on the impression produced by its external appearance. In reality, this vehicle required practically sterile conditions merely to remain operational. German engineering of the early 1940s truly adored precision. Every system here was made as if it were to be serviced by training ground instructors, not dirty, exhausted soldiers amid autumn mud. The electrics, the heart of the drivetrain, proved the most vulnerable part. Dust knocked ventilation out of order faster than the crew could remove engine compartment covers. Dirt settling on contacts led to the vehicle simply not starting after an ordinary overnight on damp ground. Short circuits, power interruptions, excessive heating, all this turned into halts. and a halt for the Ferdinand was tantamount to a sentence. Too heavy, too unwieldy, too dependent on electric motor traction, it did not know how to survive like lighter vehicles. On the front, it awaited impacts, but it was created for the laboratory. Sometimes the cause of a halt was an ordinary turn. On complex sections, in mud, or at an angle requiring fine dosing, the electric motors reacted not as the driver expected. Due to overload, one motor could shut down, and the vehicle began to crawl in the wrong direction, as if pulled by some internal, unruly force. This effect was not rare, but a familiar, almost routine problem. In peacetime, such behavior would be considered a design flaw requiring immediate rework. But war left no time for reevaluation. The vehicle had to work here and now, and any of its whims turned into lethal threats. The same paradox manifested in the armor. Yes, the 200mm frontal sheets were nearly impenetrable. This indeed made the vehicle terrifyingly resilient in direct combat. However, such armor was bought at the cost of everything else. Omission of a machine gun, worsened visibility, even greater weight, reduced maintainability. The ability to withstand a hit does not mean the ability to survive on the battlefield. The Ferdinand could take blows, but could not evade them if the running gear failed. And then the same armored giant suddenly turned into a stationary target, a besieged temple of metal held in place by its own mass. This was another internal paradox of the vehicle. Protection intended to save the crew often led to the impossibility of evacuating a damaged vehicle. Even the gun, which turned the Ferdinand into a fearsome opponent, required conditions uncharacteristic of the front. The K-43-2L71 was one of the best guns of the war, but its weight, length, and recoil constantly stressed the structure. Micro vibrations disrupted mechanism synchronization, and shells weighing 10 kilograms each turned the crew's work into heavy physical struggle in a cramped, hot casemate. With each month of service, the vehicles became not stronger, but weaker, and herein too manifested the internal contradictoriness of the entire project. Power that destroyed itself. The range, seeming acceptable on paper, in reality existed only in reports. The electrical scheme consumed fuel relentlessly, and the weight made any movement unpredictable. In dry theory, the vehicle could travel 150 kilometers on a highway, but on the Eastern Front, such conditions almost never existed. Grounds near Bryansk, Orel, Smolensk turned ideal figures into absurdity. It happened that equipment capable of destroying a tank at 2 kilometers covered only 20 kilometers in a day, not due to combat, but because the earth beneath the tracks became an enemy. All these factors together led to a clear conclusion. The Ferdinand was a weapon for pre-prepared defense, not maneuver warfare. In this, it showed astonishing results. When standing in the right position, with a field of view supplied with fuel and cover. But such conditions on the front became increasingly rare. The Germans wanted to use it as a long-range hunter, but the war forced them to employ it as a stationary bastion, and such whims of any kind turned into lethal threats. The accompanying infrastructure, prescribed on paper, in reality failed to keep up with combat. Recovery vehicles, engineers, repair platoons. All this was supposed to be nearby, but the front retreated faster than they could work. Therefore, the whims of the entire series manifested as halts and losses. And these patterns repeated again and again. Nevertheless, the legend was born. Because where conditions coincidentally aligned with the vehicle's capabilities, the Ferdinand showed itself formidable and striking. It burned T-34s, halted KV-1 attacks, hit IS-2s at distances considered fairy tales for others. And this visible power impressed so strongly that no one wanted to think that after battle, half the vehicles required repair, and some simply stood without fuel. The legend selected only those moments where the vehicle shone. Reality concealed everything else: wear, halts, crew fear. And herein lies the main point. The vehicle, conceived as a triumph of engineering, proved a living example that even a brilliant design can become an instrument of its own demise, if not fitted to the logic of war. The Ferdinand entered history not as a weapon of victory, but as a monument to how far engineering ambition can go, and how dearly one pays when this ambition collides with mud, dust, dew, torn roads, and frontline chaos. This was not just a vehicle. This was a lesson. A vehicle that could destroy the enemy, but could not conquer its own design. A vehicle in which strength and weakness lived side by side, like two halves of one truth. And precisely for this reason, the Ferdinand became a legend about how power without adaptability turns into a burden impossible to carry to the war's end. Thus concluded the service of the vehicle considered simultaneously a monster and an engineering error. It showed how dangerous the combination of outstanding armament with a design uncalculated for modern war conditions could be. At no point in its existence was the Ferdinand fully realized as intended. But in those brief periods when conditions aligned, and the vehicle had the opportunity to fire from a prepared position, it remained a threat the enemy could not ignore. Ultimately, this vehicle became part of military history, not thanks to its reliability or successes, but thanks to how clearly it demonstrated the limits of engineering solutions in war conditions, where every weakness becomes a factor of defeat.